Hello and welcome back. All right, so let me just situate the stream. Here we go. We're going to start brand new. Okay, and this is going to be 3.4. Now, this is a long chapter, and we're being introduced to a bunch of new concepts called factorials. So, what I'm going to do is probably just do the reading as the first part, and then I'm going to do the questions as the second part. All right, let's get into it. All right, let's do it. So I'm doing the reading right now, and I am going to do the examples without going nuts here. But first, regular rules apply. We're working off of Book of Proof, 3rd edition by Richard Hammock, and the download is in the description. Please get the book. It's a great book, and it is free. It's part of the Creative Commons. So I have a physical copy. It's very nice. Anyway, we are continuing from page 78. This is 3.4, factorials and permutations. I do the reading first and do examples in the book, and then afterwards I go into the questions, which here's 6 pages in, so we get to questions, something like that. Yeah, it's like 6 pages till we get to the questions, and then the exercises I'll do in the second part when I will record that as well. And as I always do it, I do the odds, so the evens, we don't damage the integrity of the book as a teaching resource. All right, let's get into it. Factorials and permutations. In working examples from the previous 2 sections, you may have noticed that we often need to count the number of non-repetitive lists of length n that are made up from n symbols. This kind of problem occurs so often that a special idea called a factorial is used to handle it. The table below motivates this. The first column lists successive integer values of n from 0 onward. The second contains a curly braces of A and B of n symbols. In the third column, they're just describing what the layout is. Basically, so here's how it works. We have n, right? N is just like when n equals to 0, how many non-repetitive lists of length 0 can we make? Meaning that we can't repeat that same list, but it has to have length 0. It's called n factorial. And the answer to that is 1, which is right here. This is going to be the empty set. Right? So, and remember how I said earlier, factorials, they just kind of assigned. I mean, I didn't know what I was talking about. This is much earlier in the book. There is this very good explanation why n factorial at 0 factorial is 1. It's because the number of sets of size 0 is 1, the empty set. Okay, so yeah, that it's not just like a random assignment. But anyway, you live, you learn, right? When n is 1. So, how many non-repetitive lists of length n can be made from the symbols of 1? So, we're going to say n factorial, in this case, is going to be 1, and the answer to that is also 1. So, and basically at that point, we're just going to use a symbol here, A. Actually, you know what? Let me just rewrite. Yeah, that's fine. So, when we write this, it would be like 1 factorial. So probably, well, I'm going to keep going like these. So you kind of get the idea for the first 2. We're going to say n equals 2. We're going to say 2 factorial, and that's going to be 1 times 2, basically. How we think about it, 1 times 2, which is equal to 2. And that's going to be, say, for example, AB and BA, just as examples they're showing us here. We get non-repetitive lists. So And then over here we have, now remember, these two are separate. If I had a comma between them, they would be the same. Like if it was A comma B and B comma A. For this kind, it would not work. But because of the way AB and versus BA is not the same thing. So here we go. So here we go. And so n is equal to 3, so 3 factorial. The way we would multiply it would be 1 times 2 times 3, which is 6. And then what we have is, they're saying A, B, C, A, C, B. I'm not going to go into the 4 one, it'd take too long. But I just want you to kind of get an idea of just like B, C, A, C, A, B, and C, B, A. Okay, so you see how that works? And then we say n is equal to 4 factorial, which is equal to 1 times 2 times 3 times 4. Okay, that's going to be 24. N equals to 5 factorial. So that's going to be 1 times 2 times 3 times 4 times 5, which is equal to 120. You see how that works? Okay. What we're doing is, this is the number of non-repetitive lists. That's the length. So basically, yeah, what we have of the symbols. Anyway, continuing on from where we're going here. Continue with the reading. For n is greater than 0, the number appears in the computed using the multiplication principle. Yeah. Okay, let's see here. This for the. Okay, the number that appears in the last column of the row is called the factorial of n. So in this case, the 1, 2, 6, 24, 120, that's called the factorial of n. So yeah, the n factorial. Or, you know, the 5 factorial is 120. Okay. So, like I was saying, in this case, instead of saying n factorial, I'm saying 5 factorial. Now, the word is, by the way, like this. Not Factorio, as in the video game. Factorial. Alright. If n is a non-negative integer, then n factorial is the number of lists of length n that can be made from the n symbols without repetition. Okay. So yeah, this is a thing that, you know, it takes a bit of playing around with. The way I generally, like when I was first learning it, I would just take the number, whatever number it is, say like 6. What is 6 factorial, right? I start with 6, and then I count down times 5, times 4, times 3, times 2, times 1, right? And that's how you do that. So basically, in this case, I already know that the first 5 is 120, and I'm going to multiply that by 6, 720. Okay, so 6 factorial is 720. All right, yeah. And then you can I just remembered that 0 factorial is 1. But the actual justification for it is because it counts the empty set. All right, so now, right, okay. So now we're saying what is example 3.8. This problem involves making lists of length 7 from the letters A, B, C, D, E, F, G. So, let's go over here. So now we are page 79. We have A, B, C, D, E, F, G. All right. How many such lists are there if repetition is not allowed? Okay. Well, so what we know is, what's the rule that we've been using? We just take the same rule. it's we count down, right? We go, what is the length of the list? Okay, so length of the list is 7. So we have 1, 2, 3, 4, 5, 6, 7. And then what we have is that we have 7 items to work with. Also 7. It just so happens this way because we're doing factorials. That's why they brought this up this way. And factorials will also work when, like, you might have a list of 20 items, but you're making a list sets of 3 or whatever. Their factorials can be all adjusted for that. We'll get to that in a minute. But basically what we're doing here is, in this case, it's a 1-for-1. So it's just a little convenient. But I had to point this out so you don't make that assumption that it's always the case. It's not. It's usually not the case. So we're going to go here is no rep. So it's just a regular rule. We drop 1 with each one. 7 times 6 times 5 times 4 times 3 times 2 times 1. Okay, so that's going to be, so we know 6 is 720. We'll just multiply that times 7. It's 540. Or sorry, 5040. Okay, so in this case, yeah, because it's a simple 1-for-1, we just did the 7 factorial. Okay. How many such lists are there if repetition is not allowed and the first 2 entries must be vowels? So this is exactly like what we had from the last time. But now, here's what we're doing. We're doing it now instead of, like sketching out the whole thing. We're going to start doing this with factorials. So, all right. Right, so there are 2 vowels here. So we have A and E. We have 2 vowels, 5 consonants. All right. And yeah, so basically, if we did that, we were going to go with, let's see here. If we did that with the multiplication principle, 2, 3, 4, 5, 6, 7. Remember last time when I did this question, I got it wrong because I didn't count out the vowels. When there's no repetition involved, if you take out the 2 vowels, you can put them into, here, to answer the question here, right? So because with the first 2 vowels are going to be, so first has 2 options, then 1. Now the vowels are gone, and there's no repetition. We cannot use the vowels in the last 5, okay? So in that case, we're down to 5 options. So we have 5. Next one's 4, 3, 2, 1. All right, so I hope that makes sense. In the first, we could have gone with A or E, and then in this case, then the remainder goes here, and then afterwards, as you can see, we have the remaining consonants, and we progressively get fewer and fewer till we're only down to our last consonant. We don't know what that one is. It kind of depends upon what you choose. But right now, we are trying to figure out what the actual possible, all the possible options we have. So we have, let's multiply that. 2 times 1 times 5, 4, 3, 2, 1. Okay, so that comes out to 240. There are 240 ways that this could be done. All right. So now, how many such lists are there in which repetition is allowed and the list must contain at least 1 repeated letter? Okay, so must contain at least 1 repeated letter. So I'm going to read this part now. To answer part C, we use the subtraction principle. Let U be the set of all the lists from A, B, C, D, E, F, G with repetition allowed. So, yeah, if we are doing repetition allowed now, so we're going to say repetitions allowed, and then we're going to say, so universe with all the possible options. And then we're going to say the cardinality of the universe, meaning all the number of lists added up. I mean, or all the number of lists. Not necessarily added up, but the point is counted up is probably the word I'm looking for. So we know that the first option is 7. There's 7 letters. We can go with anything. This is all possible combinations. 7. 7 repetitions allowed. 7 again. 7, 7, and 7. All right. So 7. There we go. All right. And that should be a 2. Wait a minute. So, right. Okay, yeah, that's correct. So far, so good. We're just getting the universe. 5, 4, 3. Okay. So, that's the universe. Now, the next thing we need to do. Okay, so right now, this contains the lists that are, let's see here, repetitive and non-repetitive. So, and what we're trying to answer right now is at least one repeated letter. So we're going to subtract from it lists that have no repetition. So remember, right now, in general, if it's a question like at least one, use the subtraction principle. At least one is a hard way to solve things. It's do the opposite, because solve the none. You know, if it's at least one, just solve the none. Be done with it. Okay, we want the none. We're going to say x is going to be no rep. Contains the x. Okay. And then we're trying to get the cardinality of what that is. So now what we're doing is, okay, well, actually, let's go to this. Set x contains no rep. And then I'm just going to clean my language a little bit here. There we go, comma. All right, and then the cardinality of x, the size of it. Okay, so we assigned it has no repetitions. So the rule applies. 2, 3, 4, 5, 6, 7. We actually have it up here. We have, it's 50-40, right? But let's just put it down here anyway. 7, 6, 5, 4, 3, 2, 1. We already multiplied it out. 50-40. All right. So now we just have to subtract it. So we're going to take that minus 50-40. Okay. So, and then we're going to say yes rep is contained in the so okay, this is a binary thing, right? If x contains no rep, the component of x contains rep, yes rep. I'm going to say yes rep. Okay, so we have repetition. So the component, remember, if you take x set and its component, you are creating the universe. So everything in this set, that the universe that you're working with, x has some portion of that universe. Everything that's not in x is all that there is in the universe, basically. So in this case, our universe is just constrained to these numbers. But so what we got is equal to, we have the cardinality of u minus the cardinality of x, which is equal to the cardinality of x top, which is equal to, we have 8, 2, 3, 5, 4, 3 minus 50, 40. It comes out to 818, 503. Alrighty, look at that. All right, we are on a roll here. Cool. By the way, if you're looking at the book, they also wrote it like this. You can do this. They wrote the cardinality bars on the outside. That's fine. that's the same thing. This is equal to, you can separate them like this. Yeah, that's totally fine. All right. Here we go. We have just blown through 2 pages. We are on a math bender here. All right. Okay, so page 80. Okay. In part A of example 3.8, we counted the number of non-repetitive lists made from all 7 of the symbols of the set X. Okay. And there were, so 7 symbols, and we made it so this is all the same thing. I'm just writing this down because we're going to be using this apparently. All right, 50, 40. All right, so each of these arrangements of this list, and when we say arrangements of the list, we are multiplying. In other words, like we're taking the list and we're like smushing them together. So, like for example, we're trying to the only thing is there has to be 7, right? So it can be A, B, C, D, E, F, G, right? That's one way we can do that, or we can go, G, F, E, D, C, B, A. It's a different arrangement, right? These two, they're not equal. So that's important. Just as A, B, C is not equal to C, B, A. Okay. Now, I mean, this is lists. This is not elements. Elements are items that are floating inside the box. Remember, this is from chapter 1. So don't get too confused. If you're jumping from chapter 1 into here, this is a little different. Just keep that in mind. Anyway, what this is called is a permutation. Okay, so permutation, okay? All right, and permutation of a set is an arrangement of all of the set's elements in a row. A list without repetition that uses every element of the set. Yeah, so basically, for example, basically it is a so we have they're showing us 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, and 3, 2, 1. Okay, yeah. So, and then, we can get the number, which is, let's see, this is 3 factorial. So there's, the option is, there's 6 ways to do it. There we go. Okay, so I'm just now that I talk about cards, but it's the same idea. If you have 4 factorial, it's 4 times 3 times 2 times 1, so you get 24, and then they show you how that works. In general, a set with n elements will have n different permutations. So here we go. Now again, unless there's special constraints placed. So if once we start having to choose. Now when I said like it's the stuff we're going to be working with it's going to be more complicated where there would be conditions placed. So the rules, we're still using factorials, but it would be like we would use multiple factorials within one equation. You'll see how it works. We'll get to that. But yeah, in general, basically, if you think of a factorial, if you think of anything like 8 factorial, just 8, 7, 6, 5, 4, 3, 2, 1, basically, like that. Okay? And saying a permutation of a set is an arrangement of its element in a row, we are speaking informally because sometimes the elements are not literally in a row. Imagine a classroom of 20 desks in 4 rows of 5 desks each. Let X, the set X, be a class of 20 students. If the students walk in and seat themselves, 1 per desk, we can regard this as a permutation of the 20 students because we could number the desks 1 through 20, and in this sense the students have arranged themselves in a list length of 20. There are 20 factorial, and give you the big number. To find out 20 factorial, just multiply from 20 times 19 on down, or just use the factorial option, factorial key on your calculator. All right. 81. Now we discuss a variation of the idea of a permutation of a set X. Imagine taking some number k less than or equal to the cardinality of x. So k is less than or equal to the size of x. Okay, let's start with that. Of the so in other words, if the set contains 3 items, then there's the set size, right? Anyway, let me just keep reading here before I get off topic here. So k is less than or equal to then the cardinality of the size x of the elements from the set x, and then arranging them in a row. The result is what we call a k permutation of x. A permutation of x is a non-repetitive list of all of the elements of x. A k permutation of x is a non-repetitive list made of k elements of x. Okay, here we go. This is where the brain melting starts. Okay, so let's see here. We're going to have k permutations. Okay, the 1 permutations of x are the lists we can make with just 1 element from x. There are 4 such lists. So, that would be A, B, C, D. The 2 permutations would be, let's see here, how must there be 12 of them? So, the 2 permutations of x are the non-repetitive lists that we can make from 2 elements of x. So, first, let's write this down real quick. So, we have 1 permutation. So, we're going to say, in this case, the k becomes 1, right? So, k equals to 1. So, we're going to say, we can go with, now, here's the thing. How many singletons can we make here? You can think of it that way. A, B, C, D. So, how many non-repetitive lists can we make of length 1? Okay? All right, well, there's 4. All right. Now, what about 2? Okay, 2 permutation. So, we're going to see how many can we make. So, we get to do, now remember how that rule we did before? We have 2, so we know in the first one we can have 4 non-repetitive times 3, so that's 12. So we know right away that it's going to be 12. And they have the list right here. I'm just going to copy that list directly down just because it'll be a pain to go through it by hand. But technically what they're doing is they're starting with the A's. A, B, A, C, A, D. Let's see here. A, B, A, C, A, D. And then we have B, A, B, C, B, D. And then C, A, C, B, C, D, D, A, D, B, D, C. All right. Okay. So, and we know the rule. If it was 3, 1, 2, 3, non-repetitive rule, so we're going to say 4 in the first, 3, 2, so that's going to be 24. Right, and then they list those out. Okay, the 4 permutations of x are the non-repetitive lists made from all 4 elements of x, and these are simply the 4 factorial. So, a 3 permutation, and again, it's just going to be the same thing, only it's going to be 3. And 4 is just 4 factorial. So if we think of k, k is the item. Let's try another example, perhaps. I'm just going to work on this. I'm going to just see if they're giving us another example here. Actually, they are. That's good. Okay. Let's keep going through this. And then let's go back and think about 0 permutations of x. They are the non-repetitive lists of length 0 made from the element of x. So that's 1. Of course, there's only one such list as the empty list. So 0 is equal to 1. Okay, and which is equal to the empty set. So that's not 0, that's 1. Now, we're going to introduce some notation. The expression P n k denotes the number of k permutations of an element set. So let's just go over what we did. So our element set, 1, 2, 3, 4. We have our element set. So this part right here is n. So I'm just going to write this thing down. This is the part you want to bash this into your brains, okay? This is the thing that's going to make a big difference if you could remember it. Okay, this part, this is the n. You just count them. So that's, you're going to be 4 here, right? And the k is this part. Okay, this part or this part. That's how much you're deciding. You want to know, k tells you, do you want to have this kind of set or do you want to have this type of set? Okay, so that's the important part. Just remember that. If you say that your set x has 4 items, A, B, C, D, right? So then it has 4. So our n, A, B, C, D, right? Then our n equals to 4. So we're going to put 4 here. And now we're going to say we want a list where it's going to be, I don't know, how about this? 0. We don't want, but it has to be, does it exist, right? We say, well, what if we say that we want it of a length 0, right? Let's do that. Well, yeah, of course there is. It's the empty set. So yeah, and there's 1 of them. Now, this right here is, this tells us the number. The P refers to the number of these things that exist. It doesn't necessarily tell you what they are. It simply tells you how many of them exist. That's important. So what it's saying is that there is 1. And what is that 1? It's that right there. Okay, so now let's do another one. Let's do here. We're going to say, I am going to look like that crazy guy. You know, like when the conspiracy theorist meme. This is going to turn into a conspiracy theorist meme very fast. Okay, so we have A, B, C, D. We have 4. So we're putting 4 in here. We want a length of 1, right? How many is that? 1, 2, 3, 4. So our answer is 4. All right, now we got this. Now, what if we go like this? We have our length 4, but we want them in sets of 2, okay? Well, then we have it right here, right? And that is, we can write them out, or we can use the rule over here. This is the rule here that we did. This is already turning into mush. I see that. But the answer to this, I'm going to take these 2 arrows out, is going to be 12. All right? And then P3, I didn't write it out here, but that's going to be 24. And then to do that one is right here. This is equal to P4, comma 3, which is equal to 24. And then we're going to say P4 is equal to 4 factorial, which is also equal to 24. Okay, so that's good. Anyway, this notation is very, very, very important to remember. Yeah, try to understand it. If you don't get this, this is going to be a big problem. So this is very important to get. Anyway, let's continue here. All right. What about, say, P4 of 5? This is a number of 5 permutations of a 4-element list. That is the number of non-repetitive length 5 lists that can be made from 4 symbols. There is no such list. So 5 is equal to 0. Why? Because we have 4 elements of a list that has to be non-repetitive by definition, and they want to have 5 items of a length of list 4. So we have 4 items to work with. By definition, if we were to fit one, we would have to repeat. Repeating is not allowed, therefore it's 0. So, yeah. All right, now, if n is greater than 0, let me take this part out. Okay, here we go. If n is greater than 0, then, write this down. N greater than 0. Then P and K can be computed using the multiplication principle. And the multiplication principle is what we've been doing. Okay. So, yeah, and basically, again, they have the diagram here. But basically, the way we would do it is like I've been saying, that I prefer just using examples. So if it's n is equal to 7, so it's going to be, this is going to be, and k, it depends upon what k is at the same time. So here we go, how they want to do this. So what we do is the n's progressively drop down. We have our first n times, let's see here, we have n minus 1 times n minus 2, and then dot, 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 right? And over here, the k over here is going to determine by n minus k plus 1. Okay, so all right. Notice that the number of choices for the ith position is n minus I plus 1. Where did I put the I position? The kth position? They're referring to the kth position. They must have put a misprint there. Where they wrote the n minus k plus 1, they're writing about n minus I plus 1. Hang on a minute. Yeah, I think that's what they're referring to. For example, the fifth position has n minus 5 plus 1, which is equal to n minus 4 choices. Continuing this pattern, the last kth entry has n minus k plus 1 choices. Therefore, p of n comma k is equal to n minus 1. Now, this stuff, it's more important to understand it than to memorize it. Memorizing is hard. Minus k plus 1. Okay, here we go. Okay, so then we have okay. So in this case, we're going to have some examples to work through. So let's say P 10, N is 10, K is 1, okay? So then let's substitute this. So we have 10, and then what we have here is going to be, it goes down to, which is equal to, because it has just the 1, it just goes to 10. All right, and that's because n minus k plus 1 just gives us the 10. All right, if we go P 10, 2, okay, so now let's fill this in. So we have, now the k tells us the number of the times we're going to go down, as you know. So we have the first one is our n, and then the k tells us we will need it a second time, right? So we're going to go like this. We're going to take it in here. We're going to say 10 minus 2 plus 1, which is equal to 9. So we're going to multiply this by 9, okay? And that's going to be 90. All right, so now P 10, 3. Okay, so n is 10. And then what we have here, again, we have n minus 1. Actually, get right here. We are going to go through 3 iterations. So yeah. And what I'm trying to say is that the 3, if we go back here, it tells us which one to stop at. The K is kind of like a stopgap, I guess you can think of it that way. So the way you can think of it, if we just go back here, let's not fill in the intermediate parts. Let's actually do, hang on, before we do this one, let's do like this. P, let's do here. There we go. Right. Okay. Let's do 10, this one right here. 4. And then we're just gonna, we know the first part starts at 10, but we want to know how many down the line we're gonna multiply, right? Well, we could actually go back here and just do it this way. Now, what I'm doing is, you could also think of it, it might be a little backwards, but I want to show you something. So if you just did it over here and you put the k in, you put the 4 plus 1, it's going to give you 7. So we know it's going to be 10, 9, 8, 7. Okay, so that's where we're going to stop. The k tells us the last digit that we're going to stop at, to multiply it at. Or another way you can think of it, as I think of it, is counting steps this way. So, but anyway, this notation, it's not super intuitive when you first encounter it. You have to really play around with it, see what it can do. And yeah, it takes some time getting used to. I would highly recommend you write this stuff. It's very hard to just remember, especially when we're going to be doing much more than that. It's not just P of the N and K. There's going to be more. And oh, actually, we're getting to that. Anyway, let's continue going here. So, what happens, though, when we have... this is a great example they have here. P, 10... 11. What happens if we go past it, right? Well, let's do that. 10 minus 11 plus 1 is 0. So that tells us we have to multiply from 10 all the way to 0. It's 9 times 8, times 1 times 0. 0. So that the math checks out, right? It works. Now, so we cannot have non-repetitive lists of length 11 when there's only 10 elements to work with. It's a contradiction. Get a drink real quick. All right. And of course, now use the word in general. P of n to the n equals n factorial. In general. I'm a little concerned when they use words like in general in math, because they're not giving us the conditions, the boundary conditions of what they mean by that. But it probably has to do with the type of numbers that you're using. Right. So essentially, it just means you're going to count it down. The steps, you take k times, you're going to multiply it. So if n is 3, we're going to do it 3 times 2 times 1. So 3 times, so that means 6, which is also equivalent to 3 factorial. So for our purposes, as an introduction to all this, we can keep this in mind, but keep in mind the word in general. That's probably going to bite us somewhere at some point. I don't know where yet, but we'll see. Okay. All right. Okay. All right. Here's another fun equation, finally. Okay. We now derive another formula from P to the N. So we're going to derive another formula from this. And one works for when k is greater than or equal to 0, but less than or equal to n, which so far has been the case. Yeah, our k cannot exceed n, and it has to be at least 0. So far, that condition has been the same condition we've been working with. Okay, with cancellation and definition of factorial. So this is a new thing they're giving us. Right. Okay, so I just need a minute. I'm going to write out this equation. All right, so then we're going to say we can have n minus 1 minus 2 n minus k plus 1. That's the under condition on that. Okay, and this is going to be the equivalence of n to the n minus 1, n minus 2, and then we're going to say n minus k plus 1. Okay. Now, I'm going to have to move this. Wait a minute. Okay, so need a minute to work through this. Okay, I'm gonna adjust a couple of things here. Okay, so we want to cancel some stuff out. And the way we're gonna do that, we're gonna multiply some stuff. So you know how when you have an equation, you actually, you know what? I'm gonna make this a little simpler for you. Let me just think of this for a minute here. Probably don't want to overdo it. Yeah, I don't want to go too crazy here. All right, so basically what we have, the n to the k plus 1, what we're trying to do is separate some stuff out. K to the n minus k plus 1. So we're going to multiply top and bottom. Go by... I'm going to say this part. I'm going to have to separate these out again. Okay, so we're going to multiply this by k plus 1 3 times 2 times 1. Okay, so now you can multiply top and bottom by any number, because that still is cancels out to 1, but you can move things around that way, and that's what we're doing here. I'm gonna fix that in a minute. Okay. Right. Let me see here real quick. Minus k. All right. And then what we have is, and then the final result is right here. It's k factorial. Okay, that's a simplified version. All right, now, and that's what happens is, let me see here. All right, good. Now, this is the formula that we want. If you don't quite get that, just roll with it. We're going to be using that formula a lot. And now we're going to say this here. let's take this. P n choose 5. Okay, so we're going to say here, what we're going to do is 8 factorial over 8 minus 5 factorial. So that's going to be 8 factorial over 3 factorial. Okay? So then what we're doing is that you can think of it as this. Let's write these out. 8, 7. And this is what that formula is about. We're just doing it with numbers now, so you can kind of see 6, 5, 4, 3, 2, 1, right? And then we have 3, 2, 1. Okay, so all we're doing right here is that the k right here, factorial, well, we did that, is at the bottom portion. Okay, that's here, and the full factorial is up there. Okay, so now all we're doing is this. We are scratching this part, and then we're going to say 8, 7, 6, 5, 4. Okay? And that's going to be 67, 20. All right? Okay. I'm doing good so far. Yeah, this is, again, we're going to be doing a lot of this, but it's just an idea that we just got introduced to permutations, and now we're doing k permutations. So, yeah, the book moves quickly. I'm not going to lie. We have one more page to do, but this is one of the densest, it's like 6 pages, chapters, and the material, it's, like, remember, each chapter is just going to load it on and load it on, and we're not even to the meat of the book. I mean, we, in a sense, we are. Like, all of this is very important, but we're not doing proofs yet. This is all tools to help us get to proofs. So, and that's in the second half of the book. Okay. All right, and here we go. And we're just gonna put down these things real quick here. So, what to remember? We have p to the n k. So, just examples, right? Let's think of a number, right? N. So we have, I don't know, let's say here we have size of 3. So if we have 3 slots, so we're going to say n equals 3. No, wait a minute. That would be k, actually. What I drew there was k. K is equal to 3. Let's see here. A, B, C, D, E. N equals to 5. This. So, there we go. So now, you see that N refers to the number of items, and then K is the number of ways we want them arranged. So that's how we do it. So we have, in this case, P of 5, 3, okay? And then we're going to say 5, 4, 3, multiply it out like that, okay? All right. All right, now, let me see here. The formula that we want to remember, and K is equal to, again, these things, it's better to understand them than it is to try to memorize a formula. That is very hard, and there's too many formulas. You have to be able to recreate them from understanding. And it's not that, like, you're not supposed to remember formula. Of course you do. But it's that if you don't understand what a formula does, it's next to impossible to effectively remember it. Like, what's actually happening, what the formula was designed to do, how it functions. Those are the things that matter. and then you can just, okay, yeah, you can just recreate it. But if you don't remember those things, if you're just like, okay, there has to be an n and an n minus 1, n minus 2, and an n minus k plus 1, and it's like, no, you can't remember that. You go to bed, tomorrow you won't know it. So it's just a countdown, right? K refers to the number of spots. If k is 4, 1, 2, k, 1, 2, 3, 4. K is equal to 4. K is equal to 2, 1, 2. K is equal to 1, 1. You see like that? But our n remains the same. So in this case, we have 5. So we have 5, 4, 3, 2. Then we have 5, 4, and we have 5. Okay? And of course, basically the results would be this: A, B, C, D, E. There are 5 ways, 1, 2, 3, 4, 5. 5 ways that you can do singletons here, or lists of items that are non-repetitive of length 1, right? And there's 20 ways to do it of length 2 with the 5, and there's gonna be 120, I think. Yeah, there's 120. To do it of length 4. 5 items of a list 4, non-repetitive. There's 120 ways to do it. So this is 5. Okay. And that's why I'm not listing that whole thing, because it would just take forever. Now, if the condition, if k, the number, the length, this refers to the length. K is important. Remember that as the number of items, the length of your list. You know, like your name. If your name has 3 letters, it's a list length of 3. See how that works? Okay. Your phone number is a list length of 7, for example, not counting the area code. In that case, a list length of 10. So we have 0, and if our list length k is at least 0 or bigger, but less than or equal to the length n. Now, this is the same boundary condition that we're used to. If it's 0, the result is going to be 1, because there's always the empty set, which refers to the list of the empty set counts as 1. So that's the only thing that we can have of list length 0. And of course, if it has the same list length as the number of items, then it's just multiply it by, you walk it down all the way to 1 and then multiply them all out. Then okay. Then P of nk n factorial over n minus k. I'm going to demonstrate this again one more time. So remember how I said if it is well, let's take the 5. Let's say here, let's say P 5, 5, right? So let's take the formula. So we're going to say 5 factorial, and over here we're going to say over n is 5 minus 5 factorial, which is equal to 120 over 1, which is equal to 120. And so basically, this also is the same thing as doing this. 5, 4, 3, 2, 1. Okay, so it's the same. Yeah, get used to this formulation. You have to really understand it, otherwise it's just going to become a big grind going forward. This idea is not going away. This is the new normal. All right. Okay, All right. 10 contestants run a marathon. All finish. There are no ties. How many different possible rankings are there for first, second, and third place? So, there are 10 contestants. So, I'm going to say 10 contestants. And then we're going to say okay, so then we have, okay, so then we have that. So now, 3 spots. So let's take out the word 10. I want numbers. So n equals to 10, k is equal to that. All right. So then we have, this can be thought as of permutation of 10, 3, okay? And which is equal to 10 times 9 times 8, which is 720. And then let's do it this way. N factorial over n minus k factorial. So we're going to say 10 factorial over 10 minus 3 factorial, which is equal to 10 factorial over 7 factorial. So that means, let's do it this way. Watch this. We're going to go 10 times 9 times 8 times 7 factorial. Keep in mind, the 7 factorial, I've split it up. It's still the same number. The 10 is not a factorial anymore. The 9 is not a factorial. The 8 is not a factorial. Only the 7 is a factorial. And the reason I did that is because I have a 7 factorial down here. I cancel them out, which is equal to 10, 9, 8, which is equal to 720. Or we can do this if that was too complicated. 7, 6, 5, 4, 3, 2, 1. And then we're going to break up the 7 factorial. 7, 6, 5, 4, 3, 2, 1. Okay? And we're just going to break those down. Okay, and that is again equal to 720. Okay. All right. Yeah. Hopefully some of that's sticking now. All right, next example. All right. You deal 5 cards off a standard 52 card deck. So, okay, 5 cards. 52 card deck. So we have 1, 2, 3, 4, 5. This is our K. And n is equal to 52. All right. And line them up in a row. How many such lineups are there that either consist of all reds or all clubs? Okay. So we want to know all reds or all clubs. Let's figure out what all the reds are. So here we go. The number of ways, I'm just reading the solution here. There are 26 red cards, right? So then, because we've done these before. I want to know how they're doing. Is like number of ways to line up 5 of them is P choose 5, right? So first thing we're going to do is we're going to do the first one, and that is, okay, find the reds. Find all red. And that's going to be here 1, 2, 3, 4, 5. And then we have, okay, let's see here, 26 red, 26 black. Okay, so now we're going to go with, now remember, when we're doing cards, it's assumed that it's non-repetitive because we pull them out of the deck. 26, 25, 24, 23, 22. All right. And we just multiply that out. That is 7, 8, 9, 3, 600. And then also P 26, 5, which is also equal to 26 factorial over 5 factorial. So if we were to break this up, that would be like this. 26 times 25, 24, 23, 22, 21, 20, 19, 18, 17, 16, 15, 14, 13, 12, 11, 10, 9, 8, 7, 6, 5 factorial over 5 factorial. And then we're going to scratch this, and then you multiply that out. And you get the same number. All right. Hang on a minute. Did I do that right? Hang on. Something's not right. No. Let me double check my work here. Seems like 26 choose 5. Oh, right. That was wrong. Let me fix that. Yeah, that number was too big. This is equal to it's n minus k factorial. So that's one of those things. This is why it's great to practice this, is because you will make mistakes and you want to be able to catch yourself. And this is how you do it. N is 26 minus 5, and then you get the factorial of that. So that means we have 26 factorial over 19 factorial. Yeah, no, 20 factorial. Yeah, 21 factorial. So which is equal to 26, 25, 24, this thing over 23, 22, over some more, 21 factorial over 21 factorial. You scratch the factorials. That's how the number ends up the same. Yeah. Okay. That's corrected. Getting back to the question. We just found the reds. Now we need to know how many club cards. There are 13 club cards in there. So again, we want to know that... Now these are two different things that we're doing here. We want to know that all the red cards, the clubs are black. So just so we know here. Okay. Okay, clubs are black cards. Good. So now, and there's 13. So again, we still have 5 slots that we can stick them in here. So we're going to go with, we can just do the old method that we've been doing, 12, 11, 10, 9, like that, and just multiply it out. Or we can say, P, I'm going to say 13 choose 5, okay? Which again is the same thing as saying 13 factorial over 13 minus 5 factorial. So that means we have 13, 12, 10, 9, 8 factorial over 8 factorial. We scratch that. All right, and that gets us, here we go, 1, 5, 4, 440. Okay, and then we just have to add them. So we're going to say plus 154, 440. Okay. Now the other thing that we can do, let's see here. So that's it. That answers that question. We just add them together. And that is equal to 8,180,040. All right. They're either all red or all club. And that, again, that is 5 iterations of 5. It has to be that in this case. Now, the other thing is, like, notice that on the one hand we can just do it like this, where we just like, okay, well, we know there's 5 slots, we just slot them in and count down like we've been doing before. We don't have to go with the extra mile with using the k-permutation notation. So yeah, we don't have to do that. It will be useful later, and it's useful to think of the two as interchangeable. They are. So that's just it. I'm just doing this as a way of explaining that it's the same thing, that and it's just to familiarize us with this point so it sticks that much better. This stuff is incredibly important. It will continue much further, so we're going to keep using that and using it and using it. Doesn't go away. All right, well, we got through it, and we're still alive. Wow, look at that. Through 6 pages of material. That was awesome. All right, well, we have the exercises I will do next time. So this was part 1 of 3.4, and then we're going to do part 2. We'll be doing the exercises, and that goes all the way to 17, so that's going to take some time. And then the next chapter, well, not as long, it's still kind of long. This whole section, they're all, well, actually the next 2 afterwards aren't too bad. All right, well, I hope you enjoyed it. See you next time.